This is the second part of a two-part series on the arithmetic of complex numbers. In the previous video, I defined complex numbers and introduced complex conjugate, and we did some basic manipulations, arithmetic operations that we performed on complex numbers, and introduced probably the most important theorem in all of mathematics, which is Euler's Identity. And now I'm going to go ahead and use what we learned in the previous video to now derive several of the trigonometric identities using complex variables, and show you how easy it is, that you don't have to cram into your memory all these different trigonometric identities when you can very easily, quickly derive them. There's no point in memorizing them. Now, in establishing identity relationships, we start with Euler's identity, or which also is known as Euler's formula. And that is that a complex number z can be represented two ways. Polar form, e to the I theta, which is cosine of theta plus I sine of theta. This is Euler's identity. Now, if we write a similar identity for the complex conjugate of z, we know that the complex conjugate of z is just minus the angle. So it's e to the minus I theta, which is cosine of theta minus I sine of theta. Minus angle, cosine of a minus angle is the same as a positive angle, and sine being an odd function is the sine of a negative angle is minus the sine of the positive angle. Cosine's an even function, sine's an odd function. Now we can write the real part of z, which is cosine of theta, which we can also write in terms of the complex conjugate and the complex number itself. So if you remember, the real part of z is z plus the conjugate of z. If we add z and the conjugate of z, the imaginary parts drop out and we end up with twice the cosine. So we divide by 2 to give us the cosine of theta. And likewise, the imaginary part of z is just going to be z minus its conjugate. If we subtract conjugate from z, the cosines go out, and I sine minus I sine is minus a minus I sine is the same as adding these two, or we get twice I times the sine. So this is twice I times the sine of theta when I add them, but I would need the imaginary part, which is just sine theta, so I divide through by 2i to get those to cancel in that fashion. So I'll just erase that there, and we'll write that as sine of theta. Now, let's also look at this in terms of exponentials. If I add z and the conjugate of z and divide by 2 in polar form, this is e to the I theta plus e to the minus I theta over 2. That's this portion here written in terms of exponentials. And the sine is z minus z conjugate, which is e to the I theta minus e to the minus I theta over 2i. Two important relationships here. This is used throughout math, and we'll see it a lot, is that this shows us how sines and cosines are related to exponentials. Sines and cosines are nothing more than exponentials raised to a complex power. Cosine is e to the I theta plus e to the minus I theta over 2. So this ties trig functions to exponentials. Very, very important relationship. Now, let's look at the property of exponents. If we take a base e and raise it to a power a and then raise that to a power b, we know from the property of exponents that we just can express the exponent as the product. So using this relationship and property of exponents, this is very, very important. Let's look at what happens when I raise e to the I theta to the nth power. Now, using the property of exponents, here's my a, here's my b. I can write this as I n theta. Very important relationship, and this is very curious. This is actually quite amazing what's happening here, because e to the I theta, this equation, we can write it in this fashion. E to the I theta raised to the n power is cosine of theta plus I sine of theta raised to the n power. E to the I theta is this right here. And then this is also equal to e to the I n theta. We can think of this as being our angle and write this as cosine of the angle, which is n theta, plus I times the sine of the angle, which is n theta. So, this is very curious. The cosine of a multiple angle can be written as the sine and the cosine of a single angle, all raised to a power n. And all we need to do now, in order to figure out what this is we need to expand this out. This is a binomial. This is of the form a plus b to the n power, where a is equal to the cosine of theta, b is equal to I sine of theta. So we need to expand this out for any given n. Now, let's see what happens when we make n equal to 2. Let's just figure out for n equals to 2. Well, when n is equal to 2, we have cosine of theta plus I sine of theta squared. N is equal to 2. And this is the cosine of 2 theta plus I times the sine of 2 theta. Well, we can expand this out. This is a binomial where it's of the form a plus b squared, which is a squared plus 2ab plus b squared. So we take the first term squared. This is cosine squared theta plus twice the product, cross product, I sine theta cosine theta, plus the last term squared, which is I sine theta squared. But we know from before that this is I squared sine squared theta, and I squared is minus 1. So this is nothing more than minus sine squared theta. So let's put everything in here. So we have, this is two real numbers, cosine squared and minus sine squared. So this forms the real part of the complex number. Cosine squared theta minus sine squared theta. And then we have plus I times, and here is the imaginary part, 2 times the sine of theta times the cosine of theta. Now this is equal to this. because I expanded this out. This is what the left side is expanded. And this is equal to cosine of 2 theta plus I times the sine of 2 theta. Now, for two complex numbers to be equal to one another, the imaginary and the real parts have to be equal. So I'll show you that here. Let's see, yeah, I guess we can get rid of this. So, if we have two complex numbers, z1 and z2, and if they're equal, z1 and z2 are equal if and only if the real part of z1 equals the real part of z2, and the imaginary part of z1 equals the imaginary part of z2. And that is, if z1 is x1 plus I y1 and z2 is x2 plus I y2, then for these two numbers to be equal, the x1 and the x2 have to be equal. That's what this statement says, is x1 equals x2. And then the imaginary parts also have to be equal, and that's what this statement says. The imaginary parts are equal, or y1 equals y2. So, what we have here are two complex numbers. We have a real part, an imaginary part, real part, and imaginary part, and they're equal. That's what this is. This part is the left-hand side, this part's the right-hand side, this part's the left-hand side. So we equal the imaginary and the real part. So we have that the cosine of 2 theta is equal to the cosine squared of theta minus sine squared theta, and that the sine of 2 theta is twice the sine of theta times the cosine of theta. So we have the first of our trig identities. This is what's called the double angle formula, is that we can express the sine and the cosine of twice an angle in terms of the single angle. So for example, if theta is 10 degrees, we can get what the cosine of 20 degrees is. The cosine of 20 degrees can be written in terms of sines and cosines of 10 degrees. Now, also, we can manipulate this a little bit because we know that sine squared theta plus cosine squared theta is equal to 1. We had that, remember, when we had a complex number that had unit magnitude. The angle is theta, and the real part is cosine theta. The imaginary part is sine theta. So by Pythagoras' theorem, that we have that the cosine squared plus the sine squared is equal to 1. And that's what this statement is. This is nothing more than a graphical representation of Euler's formula. That is, this is e to the I theta, has magnitude 1. E to the I theta is cosine theta plus I sine theta. So its magnitude, the magnitude of this, is just cosine squared plus sine squared, and we know that the magnitude of e to the I theta is 1. So we can put in now, let's solve this equation for sine squared theta. So this is 1 minus cosine squared theta, and we can write cosine squared theta in terms of sine squared theta, which is 1 minus sine squared theta. So in here, let's just get everything in terms of cosine. So for sine squared, I'm going to put in 1 minus cosine squared. So we have cosine squared minus 1 plus cosine squared. So this comes out to 2 cosine squared theta minus 1. And then in this one, or not this one, that's one way we can write it. And another way we can write it is substitute in for cosine in terms of sine. So if I've got 1 minus sine squared for cosine squared, this is 1 minus twice the sine squared. So this can also be written, let's just separate that out. So this is then, putting in for cosine squared, we have 1 minus twice sine squared theta. So now we have the double angles in terms of either sines or cosines. The cosine of 2 theta in terms of just cosine theta, sine 2 theta in terms of just sine theta. Now, one other thing that we can do here to manipulate this equation is, let's play a little substitution game. Okay, now we had that the cosine of 2 theta is the cosine squared of theta minus sine squared theta. And we also know that it's 1 minus twice sine squared theta, and is also 2 cosine squared theta minus 1 by putting in sine squared plus cosine squared equals 1 for the cosine or the sine respectively in there. So let's look at this equation. If we have cosine 2 theta is equal 1 minus twice sine squared theta, let's solve for sine squared. Sine squared theta is equal to, we bring that over and then the cosine 2 theta over, so it's 1 minus the cosine of 2 theta over 2. And then we will also do it for the cosine. So the cosine squared would be bringing the 1 over. So we have that, writing this out, is the cosine of 2 theta is equal also to 2 times cosine squared theta minus 1. Well, let's solve for cosine squared. Well, cosine squared theta is equal to 1 plus the cosine of 2 theta. I'm bringing the 1 over and dividing by 2. Now, in each of these, what we're going to do is make a substitution. We'll call 2 theta equals b, or theta equals b over 2. So wherever I have theta, I put b over 2. And so what we have here then is cosine 2 theta. 2 theta just becomes b. 2 theta, that becomes b. So that the putting in here, we have that the sine squared theta is equal what I need to solve here is this one for theta. So theta equals b over 2. So in here, we're starting with this equation. Sine squared of theta is sine squared of b over 2. And this is equal to 1 minus the cosine of 2 theta. Well, 2 theta is b over 2. Now, if I take the square root of both sides to get sine b over 2 alone, this becomes square root. And then likewise, for this equation, we have that the cosine squared theta is b over 2 is equal to 1 plus the cosine of 2 theta. Well, 2 theta is b all over 2. And again, we can take the square root of both sides. And these are called our half angle formulas. That is, we can get the sine and the cosine of 1/2 the angle in terms of the sine and the cosine of the angle. And that just follows by making this substitution. Wherever you have cosine 2 theta, that becomes b, and theta becomes b over 2 in both of these cases. This is equal to b, and theta is b over 2. Theta is b over 2, so this just becomes a b over 2. 2 times b over 2 becomes b. So you end up here with the half angle formulas. We have the double angle formulas, we have the half angle formulas. Now let's see what happens when we make the power n equal to 3. Again, we start with Euler's identity. E to the I theta is equal to the cosine of theta plus I times the sine of theta. And what we're going to do is raise each side to the power of 3. So we have e to the I theta to the third power is equal to cosine theta plus I sine theta to the third power. But we know from the property of exponents that e to the I theta to the third power is e to the I 3 theta. Now this is a new angle that we can put into the Euler's identity. E to the I theta is cosine 3 theta plus I times the sine of 3 theta. So now we need to expand this out, collect all the terms that contribute to the real part and the imaginary part, and then use the property of equal complex numbers, that in order for two complex numbers to be equal, the real parts must be the same and the imaginary parts must be the same. So once we have collected all the terms that contribute to each of the real and imaginary parts, then we equate them, and then we end up with two new identities. Now, in order to expand a binomial, this is of the form a plus b to the third power. Now, when we had a square, a second power, second order, the square, it was easy because we know how to do the squares. It's a squared plus twice the cross product, ab plus b squared. But when we end up with higher powers, it's not quite so easy. And the way we do it is we use what's called the binomial theorem. The binomial theorem tells us how to expand a binomial raised to a power. So, in the binomial theorem, if we have a plus b raised to the n power, this is the sum where r goes to 0 to n to the power n of, we have a combination that defines the coefficient, and it's a raised to the n minus r times b to the r. And we define the combination CNR as n factorial over r factorial over n minus r factorial. And if you remember right, k factorial is just k times k minus 1 times k minus 2 and so on down to 1. That is, the factorial of a number k is just the product of all the numbers from 1 to k. Now, it turns out that there's an easy way to get these coefficients without having to compute the factorials for the combination. We use what's called Pascal's triangle. And Pascal's triangle gives the coefficient for a binomial expansion. And the way we form Pascal's triangle, if you remember, is you start out with 1 and then you write down 2 1s to the left and right, and then we just keep adding 1s to the triangle, and the number to fill into the center is just the sum of the numbers to the left and to the right above. So 1 plus 1 is 2. We put down a 1. 1 plus 2 is 3. 2 plus 1 is 3. We put down a 1. Put down another 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Then another 1. We add 1. 4. 1 plus 4 is 5. 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. And then another 1. And so on. That's how you build the triangle. Now, an interesting thing is if you look at the coefficient of the second term, it's always equal to n. So the first row is for n equals 0. The next row is for n equal 1. The next is 2. The next is 3, 4, and 5. So for this particular problem, where we have cosine theta plus I sine theta raised to the third power, we're going to be using the third row here. That gives us the coefficients, and we're going to have 4 terms. Now, keep in mind here, if we look at this a little closer, we see that the powers on our a and b always sum, for each term, always sums to n. The a is n minus r, the b is r, n minus r plus r is n. So the powers for each term always sum to the power that we're taking a and b to. Now, the other thing to note here is that when r is equal to 0, the a is n and the b is 0. And then as r increases, the powers on the a decrement by 1 as the powers on b increment by 1. So we start out with the a at the n power, and for each term we decrease the power on a and increase the power on b. So that gives us a very easy way to write this thing down. Now in this case, remember, it's very important to carry the I along. Our a in this case is cosine of theta, and our b is I sine of theta. It's very important to carry the I along. These are our a and b. So what we do is we start now on row 3. We write down a 1. And then we start off with a to the third power, or our cosine theta to the third power, and I sine theta to the 0 power. The next term has a coefficient of 3. We decrement the power on the cosine, increment the power on I sine by 1. Then the next term has coefficient 3. We decrement the power on the cosine, increment the power on I sine theta. And then the last term, the coefficient is 1. We decrement the power on the cosine to 0 and increment the power on I sine theta to cubed. Now, to check ourselves, we sum up the powers. We look at the powers of each term. Should always be equal to n, or n in this case is equal to 3. So 3 and 0 is 3, 2 and 1 is 3, 1 and 2 is 3, 0 and 3 is 3. So we're okay there. Our a's are decrementing in powers as our b's are incrementing in powers. So the power sums are always equal to n. Now, anything raised to the 0 power, whether it be a constant or a number or a function, is always equal to 1. So I sine theta to the 0 power is 1, and cosine theta to the 0 power is 1. Let's simplify. We end up with, or I mean not 0, that goes to 1. So 1 times 1 cosine cubed is just cosine cubed theta, plus 3 times cosine squared theta, and we have I sine theta to the first power, so I sine theta, plus cosine, 3 times the cosine of theta. Now, we know here I sine theta squared is I squared sine squared theta, but we know that I squared is minus 1. So this now becomes minus sine theta squared. And then we add to it, cosine theta to the 0 power is 1, but here we have I cubed sine cubed theta. But remember, I cubed is just I squared times I squared is minus 1, so I cubed is a minus I. So this becomes minus I sine cubed theta. Now we have two imaginary terms. This one, we have an I, and we have an I here, and these two are real. So this term and this term combine to give us our real part. So this is now equal to the cosine cubed of theta minus 3 times the cosine of theta times the sine squared theta, plus I times, we have one I here, so we have 3 times the cosine squared of theta sine of theta, and then minus sine cubed theta. Now, we said that this is equal to this. So this part here, this is the real part, and this is equal to that real part. So this is the cosine of 3 theta, and the imaginary part is equal to the imaginary part here, and this is a sine of 3 theta. So now we can write down two identities. We have that the cosine of 3 theta is equal to cosine cubed theta minus 3 times the cosine of theta sine squared theta. And from here we have the sine of 3 theta is equal to 3 times the cosine squared theta sine of theta minus sine cubed of theta. Now we can further work on these two equations by noting the fact that we have the trig identity that the sine squared of theta plus the cosine squared of theta is equal to 1. So we'll substitute in for sine squared to get it the right hand side in terms of cosines, and the same thing here, we'll substitute in for cosine squared using sines to get everything on the right side in terms of sines. So first solve this equation for sine squared. let me yeah, I'll just put it right here. So we have the sine squared of theta is 1 minus the cosine squared of theta, and the cosine squared of theta is 1 minus the sine squared of theta. So in this equation we have sine squared, so we'll substitute this in for sine squared. So we have cosine squared, or cosine cubed theta, minus 3 times the cosine of theta times sine squared, which is 1 minus cosine squared theta. And in this equation, we'll substitute in for cosine squared. So we have 3 times the sine of theta times cosine squared, which is 1 minus sine squared theta, minus sine cubed theta. Now we can simplify the equation by combining terms. We see that this is cosine cubed minus 3 cosine times a minus 3 cosine times a minus cosine squared, so this becomes a plus 3 cosine cubed. And we have plus 3 cosine cubed plus cosine cubed to give us 4 cosine cubed theta minus 3 times the cosine of theta. So now we have the cosine of 3 theta in terms of cosines of theta. So we have a triple angle formula here, that 3 times the angle theta on the left side, and we have it expressed in terms of single thetas on the right side. And the same thing happens here. We have the sine of 3 times the sine of theta times 1, 3 times the sine of theta times minus sine squared, so this gives us minus 3 sine cubed minus sine cubed, so this gives us a minus 4 sine cubed. So this now becomes 3 times the sine of theta minus 4 times the sine cubed. So now we have our triple angle formulas. We have cosine in terms of, we could write it this way with sine and cosines, or just strictly in terms of cosines. And the same thing here, sine of 3 theta in terms of sines and cosines, or just strictly in terms of sines. To further gain experience in manipulating complex numbers, I'm going to compute the cube of sine and cosine theta by another method, a more direct method than what we just used. So again, we use Euler's formula in a way, in that remember earlier that we found that the cosine of theta is e to the I theta plus e to the minus I theta over 2, and that the sine of theta is e to the I theta minus e to the I theta minus e to the minus I theta over 2I. Now what we're going to do here is just cube both sides of the equation. So we end up with cosine cubed of theta is equal to e to the I theta plus e to the minus I theta over 2 cubed. We'll work on the cosine cubed. Now, so I don't have to be carrying 2 along. I'm going to move it over to the left-hand side. This is 2 cubed, which is 8, so this can be written as 8 times the cosine cubed of theta, which is e to the I theta plus e to the minus I theta cubed. And again, to expand this, we use Pascal's triangle. And the way we do that, just to show again, we put 1, 1, and 1, 1, 2, 1, then 1. We sum these two, that gives us 3. 2 and 1 gives us 3 and 1. This is n equal to 0, n equal to 1, n equal to 2, n equal to 3. So this is the row of the Pascal's triangle that we're going to use. The first coefficient is 1, then we have 3, 3, and 1. And remember, we start out with the a portion. This is of the form a plus b to the third power. Our a, in this case, is e to the I theta, and our b is e to the minus I theta. So we start out with the a to the third power, decrement the exponents on it by 1 for each term, and increment the exponents on the b for each term. So starting off, we have 1 times e to the I theta to the third power, e to the minus I theta to the 0 power, plus the next term is 3, the coefficient on the next term. We decrement the power on I theta and increment the power on e to the minus I theta. That becomes 1. The next term has a coefficient of 3. We're at this one. So this is e to the I theta. We decrement the power, and we have e to the minus I theta, and we increment the power. And then the last term is 1 times e to the I theta. We decrement to 0 and increment the minus I theta power to 3. So we can check ourselves to make sure that the sum of the powers on each of the terms should be equal to 3, our n, which is our n. In this case, n is equal to 3. 3 and 0 is 3. 2 and 1 is 3, 1 and 2 is 3, 0 and 3 is 3. So we probably didn't make a mistake here. Now, let's simplify. E to the minus I theta to the 0 power is 1. Anything to the 0 power is 1. And same thing, e to the I theta to the 0 power is 1. So we can write this now as, remember, e to the I theta to, say, the k power is e to the I k theta. So we can bring the powers down in with the I theta. So we have e to the I 3 theta plus 3 times e to the I 3 theta for this, or 2 theta for this one. And this is e to the minus I theta plus 3 times e to the I theta times e to the minus I 2 theta. The 2 comes in here, plus e to the minus I 3 theta. The 3 and the I theta combine. Now, we can rewrite this by combining these powers here. A base like e to the p times e to the q is e to the p plus q, another property of exponents. So we can combine those exponents and those exponents. So we write this now as e to the I 3 theta plus 3 times e, we have a positive 2 theta and a negative 1 theta, so this is a positive 1 theta, or I theta, plus 3. We have I theta positive minus 2I theta. So this combines to a minus I theta. And then we have e to the minus I3 theta. Now we notice that we have like powers here and here, except for the minus sign. So we're going to collect and combine. So we have e to the I3 theta plus e to the minus I3 theta from this term and this term. And then to that we add, an e in there. We can pull out the 3, and we have e to the I theta plus e to the minus I theta. Now, I'm going to write this. Remember, on the left side, this is 8 times the cosine cubed. I'm going to write it as 2 times 4 times the cosine cubed of theta, and bring the 2 down. I'm going to divide by 2 on each side. I have to divide each term by 2 on the right side. So we end up with 4 cosine cubed theta, 2 is equal to, we should recognize this, e to the I theta, or 3 theta, plus e to the minus I3 theta over 2. This is of this form. This is just nothing more than cosine 3 theta. So this is equal to the cosine of 3 theta plus, then we have 3 times, again, this is recognizable form. Of this form, it's cosine of a single theta. So this is the cosine of theta. So now we can solve for cosine 3 theta. The cosine of 3 theta is equal to 4 times the cosine cubed of theta. We bring this over to the left side, minus 3 times the cosine of theta. I'm now going to find the sine cubed of theta in a similar manner that we did for the cosine. So we can write this as sine theta cubed is equal to e to the I theta minus e to the minus I theta all over 2I cubed. Now, I'll write this as I'm going to bring the 2I cubed on over to the left side so I don't have to be carrying it. So 2I cubed is going to be 8I cubed. And remember, I squared is minus 1, so I cubed is minus 1 times I. So this becomes minus 8I. So bringing this over to the left-hand side, I have minus 8I sine cubed theta is equal to e to the I theta. And I'm going to write this as a plus minus e to the minus I theta cubed. Because this now is of the form a plus b to the 3rd power in our binomial expansion, binomial theorem. So a is equal to e to the minus, or I'm sorry, this is plus I theta. So a is e to the plus I theta, and our b is minus e to the minus I theta. So again, we'll use row 3 of the Pascal triangle because our n is equal to 3. And so we'll expand this. So we now have, we start out with the 3rd power. Our coefficient is 1, so it's 1 times e to the I theta cubed times e to the minus I theta to the 0 power. The next term has a coefficient of 3. So this is e to the I theta squared, e to the minus I theta, or there's a minus sign here. Our b is minus e to the minus theta, so we have a minus sign there, e to minus I theta. We raise it a power. Remember, the a's, they decrement as the b's increment in power. Our next term, the third term, has a coefficient of 3, so we have e to the I theta squared times minus e to the minus I theta, I'm sorry, not squared, but 1. We're decrementing the power here and incrementing the power on minus e to the minus I theta. Then the last term has a coefficient of 1. It's e to the I theta to the 0 power times minus e to the minus I theta to the 3rd power. And again, anything to the 0 power is equal to 1. We can simplify here because our exponents, we got e to the 3 theta plus 3 times e to the I2 theta. And here we have minus e to the minus I theta plus 3 times, we have e to the I theta. And we're squaring, we have a minus sign, so we square it, we get a positive, and we end up with e to the minus I2 theta. And then a minus e to the minus I3 theta. Now we can combine the exponents because the bases are the same. This exponent becomes e to the 2 theta minus 1 theta, or e to the I theta, and this one has e to the I theta minus e to the minus I2 theta, so this is e to the minus I theta. So writing this out, we have, in combining, we'll combine this term, or group them together. So we have e to the I3 theta minus e to the I3 theta. That's our first grouping. And now we group these. And what we have, we can pull out a minus 3. So we have minus 3. In this case, it's e to the I theta. And when we pull out a minus 3 here, the sign changes to a minus sign. This is positive, I'm sorry. So we have plus e to the minus I theta. So if we look at this, we have minus 3e to the I theta plus 3e to the minus I theta. Now, what we'll do is we'll pull out the minus 3 here and write this as e to the I3 theta minus e to the minus I3 theta minus 3 times e to the I theta. Then a minus gives us a plus, so this becomes minus e to the minus I theta. There. Now this is equal to, I'm going to split the 8 up as minus 2i times 4 times the sine cubed theta. This is minus 8i. Now I can divide through by a minus 2i on both sides. When we do that, is I can bring the minus sign up, so this will become minus there, and a minus gives us a plus. Now we recognize these forms. again, this is like a sine. This is sine of 3 theta minus sine 3 theta is this term plus 3 times this is sine of theta. The signs have a 2i in the denominator. So we can now write our, these go out. So we have 4 times the sine cubed of theta is equal to 3 times the sine of theta minus 3 times the sine of 3 theta. Okay. We don't need that there. So that's our other identity. Now, of course, we can get it in the same form as we had before, but by dividing through by 4. So if we divide each side by 4, this is all over 4. And that's exactly what we had with the or other derivation. There isn't a 3 here. What the heck did I do? That has a 3, but this does not have a 3. There's no 3 here. This is the sine of 3 theta, and the coefficient is minus 1, and that's what we have here. So, the next derivation will be the important one that we'll be using in Laplace transforms.